In the previous video, we saw how Coq defines the natural numbers with two constructors, O and S. Of course, writing O and S everywhere would get super annoying. So there is a syntactic shortcut for that in Coq. In fact, if you want to write the standard decimal numerals, you can, and those will be interpreted by Coq as exactly equivalent to the unary S and O representation. Okay, so for example, if you go ahead and check S, 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 O, so I wrote it out there, in fact, with that long unary representation, Coq is indeed, in its response, going to just abbreviate that as the numeral 4 that we're used to. Okay, so you can mix and match those wherever you want. They mean the same thing to Coq. All right, let's do a little bit of definition of other functions on natural numbers for a while now. We'll start with a little toy example, -2. So suppose we wanted to deduct 2 from a natural number n. Well, we'll do it with pattern matching here because, in fact, the natural numbers are defined as inductive data types. That's what we just did, so we can pattern match against them. So if n is O, then we'll return O again. So this is, again, the same kind of notion of a kind of truncation going on. Just like with predecessor, when we deducted 1 from 0, we were left with just 0 because that's all we could represent. Same thing here. So we'll truncate it at 0. Also have to truncate it at 1 here, right? So SO here, that's the successor of 0 or 1. Well, we can't really deduct 2 from that because that would take us down to -1, and we can't represent that as a natural number. So we'll go with O there. And well, if we had the successor of another natural number n prime, say, then we want to return n prime. So that's where all of the action is really occurring in this definition. Okay, again, if you really cared about this and thought those were going to be errors, those two cases, you're probably using the wrong data type. You should be using integers for that. We're sticking with natural numbers now, though. Okay, so what would -2 of 4 be? That would be 2, in fact. I stepped forward a little too far to see the output of it. There's the output right after that period. 2 has type nat. Other more complicated functions are going to need recursion, though. Okay, so what if we wanted to know whether a natural number was even? Of course, you might be used to doing that with some sort of built-in computational primitive in whatever language you're used to. Maybe you have a modulo operation. Maybe that's based on something that the circuit that your processor that your computer uses provides. Here, we're going to code things up from scratch, as it were, from first principles. How do you know whether a number in unary representation is even? Well, we're going to have to pattern match to do that. Okay, so the vernacular command to define a recursive function is a little different. It is not capital D definition. It is capital F fixed point. The reason for the name fixed point comes from programming languages theory. Fixed points are used to describe the meaning of recursive functions in it. Let's not get into that further right now. Take an upper level programming languages theory class if you want to learn more about that. For now, it's good enough to know that if you want to define a recursive function, you need to use fixed point. So we're going to define the recursive function even, which takes in a natural number n and returns a Boolean to tell us whether that number is even or not. How are we going to do that? We match n. If n is O, if it is 0, well, that's even. So we'll return true. If n is 1, which is the successor of O, then we will return false. So we've got the 0 case and the 1 case. Now everything else can be handled with recursion, because we could simply check whether the natural number that is 2 less than the one we're looking at is even or not. And if we deduct 2 enough times, eventually we're guaranteed to get down either to 0 or to 1. And we have a base case for each of those. So match against the successor of n prime. So there's 2 levels of successor here that we're kind of then stripping off of that n prime and asking whether n prime itself is even. So that creates a recursive call until we get down to one of these base cases. Okay, even is defined. It's recursively defined, in fact, guarded on its first argument. We'll have more to say about what that guarded notion means there. For now, let me just say it means the recursion is good. It means we're not going to have some sort of problematic case where we never reach a base case and get into some sort of infinite loop, as it were, with the recursion. Okay. We could define odd in the same way with a fixed point, or we could just say it's the negation of even of n, right? So that's a simple way to do it as well. All right. So now is 1 odd? Well, it ought to be. If we simplify the left-hand side, another case there where simple doesn't actually manage to do a simplification. We saw this happen once before. We also learned back then that reflexivity is willing to do even more simplification than simple itself. So let's try reflexivity at that point. And in fact, that does succeed. I'll come back to that in a little bit in a later video about the complexities of simple versus reflexivity. What about whether 4 is odd? That ought to be false. Again, we can prove that with reflexivity. Okay, so looks like we got at least some of these cases right. Great. Let's try another function that's recursive here and takes multiple arguments. In this case, it'll be the addition function, or I'll call it plus here. So we're trying to add together 2 natural numbers. Now, remember, these natural numbers, we're coding them up in unary. So there's not any kind of built-in notion of like plus from my CPU that I can use for this. I need to write this function myself. Or as Coq does, it puts it in the standard library. And here's the standard library definition, essentially, of plus. 2 natural numbers, n and m, that we're taking in, and we're going to return a 3rd natural number. Well, we'll do it with pattern matching, because that's really about the only thing we can do with these inductive data types right now. So match n. If n is 0 versus n is the successor of something. Those are really the only 2 cases. Okay, what if n is 0? Then we're trying to add 0 together with another natural number. Well, you already know from what you've learned about arithmetic in school that 0 plus something else should be the something else. Okay, so we're adding 0 to m here, so let's just return m. That's the base case for this recursion, when we finally like whittled away that first natural number down to nothing. Okay, but suppose the first natural number wasn't 0. Suppose it was the successor of some other natural number. Well, I could compute the result of this recursively. Because if I peel off that successor from the first argument here, what is the addition of the rest going to be? It's going to be taking 1 plus the addition of whatever was inside of that first natural number with m. Let me make that concrete here as an example. Suppose I was adding 3 together with 2. Well, then 3 here is really the successor of 2, right? Think about 3 here as the successor of 2. Well, then the result of the entire plus ought to be the successor of plus 2, 2. Right? I take off that 1 value from 3 and remember to add it in later again at the end as a kind of a tick mark or a successor in that unary representation. Okay, so I recurse on plus with that first argument now being 1 less than when it was originally passed in. Well, what that means is eventually I keep peeling off an s from it, an s from it, an s from it, and I'm kind of sticking them onto the outside. Eventually I'll get down to that base case where n is 0, and I can just return m, and I'll have a bunch of successors on the outside. So plus of 3, 2 should be 5. That gets it exactly right there. And here's what we've been saying. Plus of 3, 2 is really, well, what is 3? It's really the successor, successor, successor of O. 2 is really successor, successor O. So what does that reduce to? Well, we've got a successor that's pulled off of the 3. Right now we've only got 2 s's left in there. And now we strip off another one of those s's from inside there. We've got a successor of O. Strip off that final successor, it comes outside. Now we've got the plus of O together with those. And what is plus of O together with something? It's just that something. So that gets copied down into here. And now we've got 5 s's. Of course, that represents the natural number 5. So that's how our definition of plus works recursively. We can code up the rest of the kinds of normal operations you would expect on natural numbers in the same style. So maybe you want to implement multiplication, for example. Multiply n by m. Well, what is the result if n is 0? Of course, 0 times anything is just 0. So we'll return 0 in that case. Otherwise, much like we did with plus, we're going to recurse on the value that is being carried along with that successor constructor. But now we don't want to add in just 1 each time. We want to add in m. Right? So this is like n times we're going to add in m. just as multiplication is repeated addition, just like addition is like repeated increment or repeated successor. Okay, so multiply 3 by 3, we should get 9. In fact, we can prove that with reflexivity there. We could define the minus operation in the same way, the subtraction operation. Here we'll use a clever little trick with pattern matching that we haven't used so far. You can actually pattern match on 2 values, actually multiple values at the same time, by just writing a comma between them. This keeps us from having to write a nested pattern match, although if you want to study this a little further, you could go off and try to write the nested version of this yourself as well and compare them. So if you wanted to match n and m together at the same time, if the first one of those is 0, then I'm trying to subtract some other natural number from 0. Well, I don't have a way of representing that with natural numbers. So again, we'll truncate, we'll stop at 0. So that will be 0. Right, so if I'm trying to subtract, I've got like 0 minus 10, the result of that is going to be 0, because I can't do negative 10 with natural numbers. On the other hand, what if the right hand of these is 0? So if I've got like 10 minus 0, well, in that case, there's no subtraction to be done there, right? I'm done. There's nothing left to deduct. So I'll just return whatever the first argument was. In my example, it was 10. In this case, what I've done is I've said I don't care what the natural number inside of that is, because, in fact, what I really want to return is just this original argument. You could do it the other way. You could say like maybe successor of k here, and then you would have to write successor of k here, right? But that's maybe a little more verbose than we need to be. We already know what that number is. It's n there, so we don't really care what's inside of that successor constructor. Finally, if you've got the successor of n prime minus the successor of m prime, then we can compute the result of that recursively, because we can just cancel those two successors off the front of that and continue to decide what the result of subtracting n prime from m prime is. If that's not clear, take a moment, pause, work out the algebra of that for yourself, and it should become clear momentarily. Okay, so there's our definition of minus for the natural numbers. Of course, we don't want to have to write these function names everywhere, so we can also, as the standard library does, introduce syntactic notations for those that are infix. So we've got plus, minus, and times here. There's a little bit of arcane stuff that's necessary in order to tell Coq how to extend its syntax to parse these correctly, what the relative precedence of them is, how they're associative, and so forth. This is not something that we're going to go into how to learn to read terribly much or write yourself here, but it is in the Coq manual if you want to dig into it. Okay, so now we've got our plus and times, and we can do things like 0 plus 1 plus 1. That is, of course, a natural number. Now, notice that when we check that, it's really checking that the expression is the natural number. We haven't computed the result of that yet. Of course, the result would be 2, and 2 would be a natural number as well.